What I'm about to tell you today may change the way you see the universe. Because quantum physics reveals something extraordinary. The universe is far stranger than it first appears. Now let me ask you a question. What if the entire universe, the stars, the galaxies, you, me, even space and time themselves, are all part of a single invisible network? And what if at the foundation of that network lies quantum entanglement? At first, this might sound like science fiction. But here's what's fascinating. Much of what you're about to hear is based on experiments that have been observed and repeated in laboratories around the world. The final part of this video, however, will be a personal thought experiment built around questions that science has not yet answered. So today, we're not looking for definitive answers. Instead, we're going to ask the right questions. Is the universe really empty? For thousands of years, humanity has tried to understand the universe. The ancient Greek philosophers believed that everything was made of four elements: earth, water, air, and fire. Centuries later, we discovered the atom. For a long time, we believed the atom was the smallest indivisible building block of matter. But when we looked inside the atom, we discovered electrons, protons, and neutrons. Then we looked even deeper, and learned that protons and neutrons themselves are made of even smaller particles called quarks. All of this led us to a surprising realization. Matter isn't nearly as solid as it seems. Take a look at the table in front of you. Place your hand on it. It feels solid, doesn't it? But at the atomic scale, that table is made up mostly of empty space. Because between an atom's nucleus and its electrons, there are enormous distances relative to their size. So here's the real question. Is that empty space actually empty? And that's where things start to get interesting. The quantum world. In daily life, we live by the rules of classical physics. You drop a ball, it falls to the ground. A car slows down when you press the brakes. Clocks run in a regular, predictable way. All of these are events successfully explained by classical physics. But when we descend into the subatomic world, the rules begin to change. We cannot say exactly where an electron is at a given moment. Instead, we calculate the probability of finding it in a certain region. In the quantum world, the behavior of particles is defined by probabilities. And in some experiments, the result of the measurement we make is directly related to the behavior of the system itself. This is what makes quantum physics so extraordinary. Albert Einstein struggled to accept this picture. Because for him, nature should operate with more definite rules. He expressed this view with his famous quote, "God does not play dice." Einstein's objection was not to the mathematics of quantum mechanics, but to the idea that nature might truly behave in such a probabilistic way. Then everything became even stranger. In 1935, Einstein and his colleagues introduced a thought experiment that is now known as the EPR paradox. They asked a simple question: if two particles become quantum correlated and are then separated, does their connection continue? Let one particle stay on Earth. Send the other billions of kilometers away. When we measure one, what happens to the other? According to classical intuition, they should behave independently. But quantum mechanics said these two particles could still be described as a single quantum system. Einstein did not want to accept this idea. He called it spooky action at a distance. Because in his view, no physical influence could travel faster than the speed of light. But then the experiments were done. For decades, scientists continued testing this idea, especially from the 1980s onward. Experiments strongly supported that quantum entanglement is indeed a real phenomenon in nature. And in 2022, 3 physicists were awarded the Nobel Prize in Physics, for their pioneering work in this field. Today we know that quantum entanglement is not just a theoretical concept. It is a real quantum phenomenon, confirmed by experiments. And technologies like quantum computers are built on this very physics. But the real question begins here. Science shows us this: two particles, even without any visible connection, can form a single quantum system. So, is this idea limited only to the subatomic world? Or does it reveal a much more fundamental feature of reality itself? What if the stars, galaxies, matter, space, and time are all parts of a larger structure we do not yet fully understand? Today, we don't know the answer to this. But modern physics brings us right to the edge of these questions. And exactly here, another mystery appears. Perhaps, an even greater mystery than quantum entanglement itself. Because today, we can observe objects billions of light years away. We can image the surroundings of black holes. We can measure the cosmic microwave background radiation left over from the early universe. Yet despite all of this, we still don't know what most of the universe is made of. The stars we can see, the planets, the galaxies, and even you, make up only about 5% of the universe. The remaining 95%, we cannot observe directly. It does not emit light. It does not reflect light in any way we understand. But we can measure its effects. It's as if something invisible is shaping the large-scale behavior of the universe. We call part of this invisible influence dark matter, and the other part, dark energy. So why are scientists so certain these things exist? If we cannot see them directly, how can we know they're there? Now we arrive at perhaps the most interesting part of the story. Imagine this. When you look at the night sky, you see thousands of stars. With telescopes, you see millions of galaxies. And today, thanks to the James Webb Space Telescope, we can even see billions of light years away. Naturally, a person thinks, this is the universe. But actually, no. Everything we see is only a tiny fraction of the universe. Now I want to take you back about 90 years. In the 1930s, astronomers began studying galaxies. One of them, a Swiss astronomer named Fritz Zwicky, made an interesting calculation. He was examining the motions of large clusters of galaxies. Using Newton's laws of gravity, he thought, if this is the amount of visible matter, then galaxies should be moving at these speeds. But the numbers didn't match. The galaxies were moving much faster than they should. Under normal conditions, galaxies moving that fast should tear away from each other and scatter into space. But they weren't scattering. It was as if a giant invisible hand was holding them together. Zwicky called this invisible mass dark matter. At the time, no one took it very seriously. Many scientists thought it was simply a calculation error. But years passed, and another astronomer, Vera Rubin, began studying different galaxies. Her observations would completely change the world of science. Imagine a galaxy. At the center, there is a dense region containing billions of stars. Around it, other stars orbit. You can think of it like the solar system. Mercury, Venus, Earth, Mars, all orbit around the Sun. And we know that as you move farther from the Sun, the orbital speeds of the planets decrease, because gravity weakens with distance. Scientists expected the same to be true for galaxies. Stars closer to the center should orbit faster. Stars farther out should orbit more slowly. But observations showed the exact opposite. The stars at the outer edges of galaxies were orbiting almost as fast as the stars near the center. This seemed impossible. Because there wasn't enough matter, at least not the matter we could see, to hold them at those speeds. This is where scientists reached an important conclusion: maybe there was an enormous amount of matter we simply couldn't see. And this matter was surrounding galaxies like an invisible halo. Today, we call this the dark matter halo. But the story doesn't end here. Because we still haven't seen dark matter. We haven't photographed it with any telescope. No one has ever held it in a laboratory and said, here it is. This is dark matter. So why is science still so certain that dark matter exists? Because sometimes you don't need to see something directly. Seeing its effects is enough. You can't see the wind, but you can see the leaves moving. You can't see gravity, but you can see the pen falling from your hand. You can't see electricity, but you can see the light bulb glowing. Dark matter is similar to this. We can't observe it directly, but it affects everything around it. And these effects appear not in just one galaxy, but in thousands of galaxies, consistently, across millions of light years. That's why scientists don't say, we have seen dark matter. They say, we see the effects of dark matter. And these two sentences are actually very different. But, just when everyone thought, maybe we've solved the mystery, the universe surprised scientists once again. Because dark matter wasn't the only invisible thing. There was something even stranger. Something that didn't hold galaxies together, but instead was pushing the entire universe apart. And this is where dark energy enters the stage. At first glance, it sounds like the same thing as dark matter. Both are dark. Both are invisible. But in reality, they behave almost like opposites. Dark matter holds matter together. Dark energy, on the other hand, pushes the universe apart. To understand this, we need to go back about 100 years. When Albert Einstein published his theory of general relativity in 1915, he noticed an interesting problem about the universe. His equation said this: the universe must either be expanding or contracting. Because gravity pulls everything toward everything else. But at that time, people believed the universe existed eternally in a fixed state. It wasn't expanding or shrinking. Einstein added a small adjustment to his equations to match this idea. Today, we call it the cosmological constant. It was essentially a mathematical balancing factor. It countered the attractive force of gravity with a slight repulsive effect. But soon after, in 1929, American astronomer Edwin Hubble made one of the most important discoveries in history. When he looked at the galaxies in the sky, he noticed that all of them were moving away from us. And even more interesting, the farther they were, the faster they were receding. When we first hear this, it might sound strange. But let's think of a simple example. Take a balloon. Draw a few dots on it with a pen. Now slowly inflate the balloon. What happens? None of the dots move on their own. But as the balloon expands, the distance between the dots increases. And the dots that are farthest apart seem to move away from each other faster. Because the thing that's growing isn't the dots, it's the balloon itself. This is how scientists think about the universe today. Galaxies aren't traveling through empty space. More precisely, space itself is expanding. So galaxies aren't moving away from each other because they're flying through space, they're being carried apart by the expansion of space itself. This discovery led to the birth of the idea of the Big Bang. Because if the universe is expanding today, then in the past it must have been smaller. And if we go far enough back, everything reaches a single beginning, incredibly dense and incredibly hot. Today, we call this the Big Bang. But the story doesn't end here. The real surprise comes next. In the late 1990s, scientists began studying very distant galaxies. Their goal was simple: the universe is expanding, fine. But is this expansion slowing down over time? After all, billions of galaxies are pulling on each other, just like a ball you throw into the air. As the ball rises, gravity slows it down. Scientists expected the same for the universe. Maybe the expansion was continuing, but gradually slowing. But the result was the exact opposite. The universe wasn't slowing down. It was speeding up. When scientists first saw this, many thought, there must be a mistake in the calculations. Because this was a completely unexpected result. But they checked again. Measured again. Calculated again. The result didn't change. The universe was expanding faster and faster. And at that moment, a new mystery appeared before science. What was causing this acceleration? No one knew. They needed a name for this unknown effect. And that's why they called it dark energy. Here, there is a very important detail. Most people think, dark energy was discovered. No. What was discovered wasn't an energy. What was discovered was that the universe was behaving differently than expected. Dark energy is simply the name given to this unknown effect. So to be honest, science still says this today: we observe an effect that accelerates the expansion of the universe. But we do not yet know exactly what it is. And I think this is where the most fascinating part begins. Because if you noticed, both dark matter and dark energy are invisible. We cannot observe either of them directly. We only know them from the traces they leave behind. And now it's time to ask a new question: what if the effects we see in the universe are actually signs of a much deeper principle we haven't discovered yet? Maybe what we call dark matter and dark energy today are simply symptoms of a deeper physical structure we don't fully understand yet. Science sometimes moves forward not with answers, but with the right questions. And right at this point, quantum physics steps back onto the stage. The human mind tries to understand the universe through everyday experiences. You drop a stone. It falls to the ground. You push a glass off the table. It breaks. Cause, effect. Everything is clear. But the moment you descend into the world of atoms, this certainty disappears. It is replaced by probabilities. Think of an electron. Today, no scientist can tell you, an electron is exactly right here. Instead, they say, we have a high probability of finding the electron in this region. So, nature may not behave as precisely as we think. At first, this feels unsettling. Because the human brain doesn't like uncertainty. But experiments repeatedly show the same result. Now I'll ask you a very interesting question. Imagine an orchestra. 100 people playing music at the same time. Each with their own instrument. Violin. Piano. Cello. Flute. Yet all of them create a single symphony. So, could the universe be like this too? Billions of particles, perhaps parts of one grand system. This is where quantum entanglement becomes fascinating. Scientists can entangle two particles. This is no longer a debated theory. It is a quantum phenomenon repeatedly confirmed through laboratory experiments. Then these particles are separated. And still, their quantum states cannot be defined independently. The system must be treated as a single quantum state. This situation was so extraordinary that even Einstein didn't want to accept it. Because our classical intuition tells us everything should be independent. But quantum physics sometimes shows us the exact opposite. Now let's pause and think. What has science told us? Two particles can form a single quantum system. So, how far can this idea extend? 2 particles. 100 particles. Millions. Today in laboratories, not just 2 particles, but quantum systems containing many atoms can be created. And the working principle of quantum computers already comes from this very idea. So the question is no longer, does entanglement exist? The real question is this: what is the limit of this effect in nature? And this is exactly where science cannot yet give a definitive answer. Some physicists have begun asking much bolder questions. What if space is not as empty as we think? What if spacetime is actually the result of a deeper quantum structure? Some theoretical studies explore whether there could be profound connections between the geometry of spacetime and quantum entanglement. These studies are intriguing, but they have not yet been experimentally confirmed. So these are ideas science is exploring. not established truths. Hearing this inevitably brings another question to mind. If at the most fundamental level of reality, everything obeys quantum laws, why don't we feel this in the macroscopic world? Why don't tables, walls, mountains, and people behave like quantum objects? The answer is sought in a process called quantum decoherence. Because we are constantly interacting with our environment, quantum behaviors become extremely difficult to observe on large scales. That's why everyday life appears classical. But this does not mean quantum physics disappears. It simply means its effects look different at large scales. And right here, perhaps it's time to ask the most important question of the video. What if quantum entanglement is not just a strange feature we see in the subatomic world? What if this is just a small window into a much larger structure governing how the universe works? For now, we don't know. And to be honest, science doesn't know either. But history shows us that sometimes the greatest discoveries begin with the questions someone dares to ask. And now, I want to ask you such a question. Perhaps the most controversial question of this entire video. What if dark matter, dark energy, and quantum entanglement are not completely separate things? What if they are all different faces of a deeper physical truth we haven't even named yet? Let me say this again. What I'm about to describe is not a conclusion accepted by science today. It is a thought experiment I've been contemplating for a long time. A hypothesis. It might be right. It might be wrong. But perhaps it can lead us to new questions. Because sometimes, what moves humanity forward is not the answers, but the questions. Now, I want you to join me in a short thought experiment. Since the beginning of the video, we've talked about three different mysteries: quantum entanglement, dark matter, and dark energy. At first glance, we might think these are completely separate topics. But the question that keeps bothering me starts exactly here. What if these are actually different reflections of the same underlying truth? Quantum entanglement shows us that two particles, no matter how far apart they are, can form a single quantum system. We cannot directly see dark matter, but we observe its gravitational effects on galaxies. We cannot see dark energy either, but we can measure that the universe is expanding faster and faster. Three different phenomena. Three different mysteries. And their common point is this: we see their effects, but we still don't know their fundamental causes. This is where my thought experiment begins. Today, some interpretations of physics suggest that every quantum possibility might occur in a different universe. Is this true? We don't know. There is currently no experimental evidence to confirm it. But just for a few minutes, let's assume it is true. If every quantum possibility really creates a new universe, then reality could be imagined as a gigantic tree that constantly branches out. Every possibility, every quantum event, could be adding a new branch to this tree. And we might be living on just one of those branches. Now let's come to the main question. Scientists today observe that the universe is expanding at an accelerating rate. Because they cannot explain this observation, they call it dark energy. But that name is not the explanation itself. It is simply a label we give to a phenomenon we cannot yet understand. Here's the question that comes to my mind: could the expansion we observe be the large-scale result of constantly emerging new possibilities and new universes? In other words, we think we are looking at a single expanding universe. But what we see might be only a small part of a much larger reality. This thought brings me back to quantum entanglement. Because if reality is not made of independent pieces, the way we assume, then quantum entanglement may not be just an interesting event. Between two particles. Perhaps it is the first clue to the fundamental connection mechanism of the universe. Particles may not be linking to each other later on. Maybe they have always been parts of the same whole. I want to emphasize again, what I'm describing is not an accepted physics theory today. It is my personal thought experiment. It could be wrong. It could be incomplete. A completely different explanation might emerge. But the history of science teaches us something important. Many ideas we consider absolutely true today were once just hypotheses. Maybe in the future, we will explain dark matter and dark energy in ways very different from today. Maybe we will understand that both are consequences of a deeper physical structure we haven't discovered yet. We don't know this today, but the questions worth exploring emerge exactly here. And the question that occupies my mind the most is this: does the universe truly consist of independent objects? Or have we been looking at different parts of a single whole from the very beginning? If the second possibility is true, then we must also change how we think about quantum entanglement. Because in that case, quantum entanglement is not a mechanism that creates the universe, it might be the most fundamental property of the universe itself. And maybe the common point of all these unanswered questions is the very first question we dare to ask. Humanity, since the first day it looked up at the sky, has been chasing the same question: how did the universe come into existence? Every era could answer this question only as much as its knowledge allowed. Once, we thought the stars were the fire of the gods. Then we learned they also obey physical laws. We discovered the atom. Then we saw that even the atom could be split. We discovered galaxies. We discovered black holes. We discovered gravitational waves. And every new discovery showed that the universe is far more complex than we imagined. Today, we are at a similar point. We do not fully know what dark matter is. We do not know what dark energy is. And we still do not fully understand the role of quantum entanglement at the foundation of reality. Perhaps all these mysteries are different faces of a single physical truth we have not yet discovered. We cannot say this today. But it is certainly a question worth exploring. In this video, I shared my own thought experiment with you. I explained that quantum entanglement might not be just an interesting quantum event between two particles, but could be the fundamental connection structure of the universe. If reality truly works this way, the multiverse, and the phenomenon we currently call dark energy, might be results of the same structure, appearing at different scales. This is not an accepted theory today. But in my view, it is a question worth asking. Science does not begin with definite answers. It begins with the right questions. And sometimes, a single idea can become the first step toward a completely different discovery years later. Maybe this idea will turn out to be wrong. Maybe it will remain incomplete. Or perhaps a completely different explanation will be found. All of these are possible. Because the strongest aspect of science is that it can be proven wrong. So, I don't want you to leave this video with a definitive answer in your mind. I want you to leave with just one question. What if quantum entanglement is not an event happening inside the universe? What if the universe itself is built upon quantum entanglement? Maybe the answer to this question will not be seen by us. But humanity has made all of its great discoveries because it dared to ask questions like this. Perhaps, the next great discovery will begin with the curiosity of someone who is carrying this very question in their mind right now. I simply shared my own thought experiment. The decision, I leave to you. Because sometimes a discovery begins not by finding the right answer, but by asking the right question. The scientific information presented in this video is based on research supported by current experiments and observations. The views shared in the final section, however, are a personal thought experiment, not an accepted scientific theory. My aim is not to reach a conclusion, but to encourage scientific curiosity and questioning.